Gunpowder sounds like a material that should work better the finer it is. Finer powder usually means faster reactions. Much like powdered sugar, ignites more easily than sugar cubes because the surface area is vastly larger. Yet black powder follows a counterintuitive rule. Grind it too fine, and it burns, slower and less reliably. For centuries, workshops settled on grain sizes between roughly 1–3 millimeters. That tiny measurement about the width of a toothpick tip became the foundation of every smoothbore firearm of the medieval era, because it determined burn rate and the force pushing the projectile forward. This unusual standard came from repeated experimentation. Craftsmen noticed that overly fine powder compacted too easily, forming dense masses inside the barrel that prevented flame from spreading. The idea sounds simple, but the consequences reshaped weapon design. A grain size shift of only a few percent could change the entire reaction dynamics. To understand why 3 millimeters became the balance point, we have to trace the manufacturing cycle backward, from grinding and mixing to pressing, and finally, corning. The three components of black powder saltpeter, charcoal, and sulfur were originally ground as finely as possible. Crystalline saltpeter might begin at several hundred microns, then shrink to only a few dozen microns after milling. Reducing particle size by 10 times can increase surface area nearly 100-fold, allowing reactions to occur faster and more evenly. Sulfur is soft and fractures easily, while charcoal is porous, moisture-absorbing, and filled with microscopic channels that help ignition spread quickly. Once all three powders reach a texture close to cosmetic powder, they are chemically primed for rapid oxidation. The problem appears immediately after grinding. Ultra-fine powder traps moisture more easily, and even the weight of the material itself can compress it into dense layers, similar to how pressing a spoon onto cocoa powder leaves a compacted patch inside gunpowder. Such density is disastrous. Flame travels mainly across surfaces, and without gaps between particles. The fire loses its path. The result is a sluggish burn, reduced gas production, and weaker shots. Early manufacturers realized that fineness was only half the story. The other half was creating a structure that allowed flame to run between particles. Achieving that structure meant transforming powder into grains, and at that point, the technical path branched into an entirely new direction. And granulation was invented to solve the paradox. Finer powder ignites easily, but finer powder also clogs. By adding a small amount of water and pressing the mixture through screens, makers formed clusters about 1–3 millimeters in diameter. The gaps between grains created a natural network of airflow. Flame propagation depended not only on chemical contact, but also on empty space. If each grain produced a thin ash layer as it burned, those gaps allowed heat to pass through and ignite neighboring grains. The 3 millimeter size represents a clear balance. Below roughly 1 millimeter, grains lose structural strength and crumble back into fine dust, recreating the original problems. Above 3 millimeters, the reaction zone inside each grain becomes too thick, slowing combustion. Oversized grains behave like tiny pieces of firewood, burning from the outside inward and reducing the speed needed to propel a projectile out of the barrel. Smaller grains help heat spread quickly. Larger grains stabilize the reaction and prevent excessive compaction. The 1–3 millimeters range optimizes both goals at once. Historical gunsmiths discovered this through repeated testing, increasing grain diameter from 2.5 mm to 3.5 mm noticeably reduced projectile velocity in the same firearm. Shrinking grains to around 1 mm increased uneven burning and caused inconsistent shots. Granulation did more than optimize burn speed. It opened the door to the next innovation, corning the process that made grains more stable and uniform. Corning involved compressing the mixed powder into a solid cake and then breaking it apart to create hard, consistent grains. Pressing forced the components together, reducing the risk of separation during transport. Without this step, Vibration over long distances caused heavier saltpeter to settle at the bottom, while charcoal and sulfur rose to the top. A separated batch of powder burned unpredictably. Nitrate-rich areas flared intensely, while nitrate-poor areas burned slowly, creating uneven pressure inside the barrel. The pressed cake gained a certain rigidity. When shattered, it broke into fragments that retained the same internal ratio of ingredients. Each 3 mm grain became a miniature version of the entire mixture, a tiny reaction engine containing enough saltpeter to provide oxygen, enough charcoal to release heat, and enough sulfur to lower ignition temperature. Corning also controlled density. Corned powder grains were typically denser than loosely granulated powder, delivering more energy per unit volume. In early firearms, where combustion chamber space was limited, increasing energy per cubic centimeter allowed higher projectile speeds without altering barrel design. When European workshops standardized Corning in the 17th century, firearm performance improved dramatically. Matchlock muskets evolved from unpredictable tools into more consistent military weapons, stable enough to reshape battlefield tactics. If you want to explore further into the world of materials that appear simple but operate under surprisingly complex logic, the next chapter dives into the self-oxidizing behavior of saltpeter, the reason gunpowder can burn even when fresh air struggles to reach it. Follow along to keep the rhythm, and let physics and chemistry tell the rest of the story.